Okay, so I'm going to finish up with backprop. There was a mistake in my equation last time, I believe. And in particular, I'm going to talk about biological plausibility. So backprop, standard backprop is not biologically plausible, but there may be ways to fix that. And then I'm going to tell you about transformers. So transformers are super popular these days. They underlie ChatGPT, the giant transformer. And they're not that different. Well, they're kind of different. But they have the same idea of standard feed-forward networks, just a different architecture. Then I'm going to tell you about unsupervised learning. So for backprop, you need training examples. So you need labeled data, which is not really the way the brain works. For transformers, you can actually run those in unsupervised mode. You do need training data, but it's easier to get. But in fact, the brain, all the learning is really technically completely unsupervised. All you get are input spikes. There's no teacher telling you what's right or wrong. You sort of develop teachers because you have language. But in fact, everything has to be unsupervised. So I'll talk a little bit about unsupervised learning. And it's kind of, it's usual thing. We're going to write down a cost function, but it's a very different cost function. And in many ways, it's much, much harder. Okay. Oh, and then after that, we're going to talk about, we're going to switch gears and talk about reinforcement learning. Well, not exactly a switching gears. Reinforcement learning is unsupervised, but in unsupervised learning, you kind of get maybe a useful feedback signal. In reinforcement learning, your only feedback signal is reward. You know, what you did was good or bad. Okay. So let's finish up with backprop. I'll go to a new page. So remember, we're considering deep networks to this form. They can have many layers. The input layer here in layer 1 is X. So this is layer L. And the transformation from layer L to layer L+1 is X in layer L, say in layer L from L-1 to L equals some function, often just a threshold linear unit called the ReLU of W. Actually, I'm going to call this of HL, where HL equals W L dot X L-1. And in terms of indices, we can write this as Xi in layer L equals phi of Hi in layer L. And then Hi in layer L is a sum on J of W I J. That's a weight from L to L-1 to L times X J L L-1. So if this is layer L, put this in. So the weights from layer L to L+1, actually weights from layer L-1 to L. So these weights would be WL. It's a vector. And then over in here, you'd have X, L-1. Then layer L, you would have XL. Okay. So it's a relatively simple transformation. The training examples are, so if you call this thing in the output, this is f as a function of all the weights, and the input, call this equals y. So your training examples are x mu, y mu, and y mu might be linear regression. It might be log loss. It could be lots of things. Well, so y mu is, and so what we want to do is minimize. The goal is to minimize loss. So mu equals 1 to p. And the loss, L, which depends only on the weights, is 1 over p, the sum, mu equals 1 to p, of some loss function that depends on y mu and f of w, comma x mu. So this loss might be, for instance, so square loss is common. So this would be 1/2 y mu minus f of w, comma x mu squared. And there's also, you might, for labels, it might be log loss. If y mu is 0, 1, so labels, 0, 1 labels. So the output f in that case has to be between 0 and 1, and the loss is called log loss, is minus y mu log f of w, comma x mu, minus 1 minus y mu log 1 minus f. Okay. And so if when this encourages if y mu equals, so if y mu equals 1, this is largest when f mu is also equal to 1. And if y mu equals 0, this is larger when f is also equal to 0. Okay. But you know, you can have any kind of loss you want. Okay, and what we're going to do is run gradient descent. So under gradient descent, so gradient descent, the update, the change in the weight, this is full gradient descent, is equals minus eta partial of L with respect to W. This is in general, and we saw before that implies that delta L, the change in the loss for small learning rates, equals minus eta partial of L with respect to W dot partial of L with respect to W for eta small. So we saw that last time. It's easy to show. Okay. Now the problem, of course, is that we have a very complicated function, right? So it's a function that starts here, it goes through multiple layers. It starts here, nonlinearity, 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 and finally an output. And so taking this derivative, it's not obvious that it can be done, but people have shown it's possible. This was invented and reinvented many times. So what I want to do is basically take a derivative in layer L. Okay. And how do we do that? I'm going to use components. So I'm going to take, I want to compute partial of L with respect to W I J L. And remember that WIJL is given, well, HI is function of WIJL and XJL minus 1. So this becomes equals partial of L with respect to HIL times XJL minus 1. So from HIL equals the sum on J to the sum on K of W I K L X K L minus 1. So this term XJ L minus 1 is basically the chain rule. This is a partial of H I L with respect to W I J L. Okay. We differentiate this with respect to WIJL, you just get it out of XJL minus 1. So what we want to do is backprop this error WIJL. So we write it as, I'm going to define this to be delta IL. So this is our backprop error signal we need to compute. The neuron has access, obviously, a synapse has access to its presynaptic firing. But what we want to do is now compute this. And we're going to write delta IL is equal to so partial of L with respect to HIL, of course. And we're going to write this as a sum on J of partial of L with respect to HJL plus 1 partial of HJL plus 1 with respect to HIL. And the idea is that what we're doing is, okay, we want to compute the error in this layer. So the error in this layer is related to the error in the previous layer, which should be closer to the final error. So the error in the output layer is really easy to compute, right? Because we just know how it affects the output. The error here is a little harder, but if we know how the error changes in activity here affect the output layer, we should be able to figure out how change in activity here affects the output layer. And we'll see that in much more detail soon. Okay, so remember that XKL minus 1. So actually I'm going to write over here, I'm going to write HI or HJL plus 1 equals the sum on I or sum on K of W I K L H X K L minus 1. Remember, X K L minus 1 is nothing but an XKL is nonlinearity of HKL. Okay. So now, if we look at this, the partial of HJL plus 1 with respect to HIL is really easy. So this term here is equal to, just from up here, is W J I L plus 1 times phi prime of HIL. Okay. When we differentiate with respect to HIL, we only pick out the term with K equal to I. With K, sorry, oh, I cannot write today. H J K. Okay. So we differentiate this term with respect to HIL. The only term that survives in this is when K equal to I. Okay. And so what we get is the sum on J. So this term here, by definition, is just the backprop error signal, right? This is delta I, delta J with an L plus 1. So delta J L plus 1 times W J I L plus 1 phi prime of H I L. Okay. So this is basically, this is backprop. This is why tech is taking over the world. The simple chain rule equation. So what I want to talk about now is I want to give you a little bit more intuition for this. And then we'll talk about how the brain might implement it. Okay. And so what you can see from this is basically to update the error signal in layer L, you have to know that the weights, neuron I in layer L, you have to know the weights from I to the next layer. Okay, so the neuron has to know its outgoing weights. And it's kind of useful to get some intuition for that. We'll consider a neuron here. This is HI. The activity here is HI in layer L. Okay, it's got a bunch of inputs from X L minus 1. Okay. But it's also got outputs to the next layer. So these are the W's L plus 1. And inside here are H L plus 1. Okay. And so the question a neuron has to ask when it gets when deciding on whether or not to change its weights, right? So basically you have some weights, WL. So the question, should I change my weights, is the same question as, should I increase or decrease my activity? Okay, it's really exactly the same question because the neuron knows the value of X. So if it wants to increase its activity and X is positive, it's going to make the change in weight positive. Want to decrease its activity when X is positive, it'll make this weight negative. Okay. So the weight change is the answer to the question, is my phi weight too high or too low? So let's see what happens when we let HIL go to HIL plus delta HIL. Okay. So what happens to the activity out here? Okay. We can look at activity. We'll look at activity in one of these things. Call it HJL plus 1. So how does HJL plus 1 change when HIL goes to change it by a little bit? So remember, HJL plus 1 equals the sum on K of W I K L plus 1 phi of H K L. Okay. So we're only changing HI. Okay. So HJ L plus 1 goes to HJ, basically the sum on K of K not equal to I of WIK L plus 1 phi of HKL plus the only thing that really changes is W simply cannot get this right. This is JK. plus WJI L plus 1 phi of HIL plus delta HIL. Okay. Remember, HI is changed by a little bit, so only this term changes. And this term now, if the change is small, this term is approximately equal to phi of HIL plus phi prime of HIL delta HIL. Okay. So what that means is HJ L plus 1 goes to HJ L plus 1 plus W J I L plus 1 phi prime of HIL delta HIL. Okay. And this is exactly the term we see in our backprop rule. So if you go back to the backprop rule, it's WJI L plus 1 phi prime. Okay. And that's basically because that's the effect changing this has on the activity in the next layer. Okay. So really what's important about this is the neuron, if the neuron wants to know whether to change its weights, it has to know its outgoing weights. Okay. And so there are now two reasons why backprop is not biologically plausible. So for backprop in the brain, so we can now think about backprop in the brain. To run backprop in the brain, neurons need to know their outgoing weights. Their outgoing weights. Okay. So they don't. 500 million years of evolution, a neuron spikes, it has no idea what's going to happen. Sort of, we're going to come back to that. But they certainly don't know the outgoing weights to this detail. They don't really know, this is a weight from I to J, neuron doesn't know what it is. Okay, that's happening, that's a synaptic strength way over here. The other thing is, if you look at backprop, if you look at the update rule, this is a network going backwards. Okay, so it starts in the output layer, it starts in layer L plus 1, it goes backwards. So we're running, sort of in some sense, we're running a different network backwards. Okay, backprop starts here, goes there, goes there, goes there, goes there, goes there. And importantly, as it backprops, if you look at the equation, it has to know the activity in the forward pass. Okay, so to run backprop, there has to be a forward pass. And he also needs a backwards pass while keeping in the forward pass. Okay, so the backward pass uses different variables, right? The backward pass basically computes these. This is what gets computed in the backwards pass, right? So it basically is a network that computes these deltas, and they're based on the activity in the forward pass. And of course, it has to remember its activity to update the weights. So it's a really complicated process. Now, and so the brain, so certainly this version of the brain, it really cannot run Backprop, okay? However, it turns out that there are some approximations it can make. So remember early on, we saw that neurons are either excitatory or inhibitory. And it turns out, so if you look at the brain, here's your brain, better brain than that. Here's your brain. If you look at, brains are divided into areas. If you look at the projections from one area to the next, so long range projections are always excitatory. In the cortex. Now, in subcortical areas, there are exceptions, but as far as I know, any particular area either sends all excitatory out, use all excitatory connections or all inhibitory connections. But for the cortex, it's always excitatory. So why is that important? So it turns out that mainly what you need is the sign of the weights. So remember, so actually I'm going to write down our learning rule. So if you update weights according to delta W in layer L, really should be a matrix, equals minus eta partial of L with respect to WL, and we saw this equal to minus eta partial of L with respect to HL times XL, L minus 1. Okay, we're going back to vectors, okay? Suppose though, so this is what we want the signal to be. Suppose we change it by set to something else. Minus eta, I'm gonna call this delta L hat, which is some estimate of the true backprop error signal, XL minus 1. So remember delta L is a true backprop, true error signal. And that equals the partial of L with respect to HL. A derivative that's very hard to compute, okay? So now what happens if we run this approximate backprop signal? The change in the weights is going to be L of W plus delta, well, kind of bad notation. So it's going to be L of W. We'll do the sum on L of W plus delta WL minus L of W. And this is equal to the sum on L small learning rates minus, small learning rates, this is approximately equal to minus eta the sum on L of partial of L with respect to W times delta W equals minus eta the sum on L. So a partial of L is a dot product here. It's a giant dot product involving matrices, but we can write partial of L with respect to HL times our learning rule now involves this delta L hat. Dot delta hat L. And then it's this other term, XL minus 1. XL minus 1 dot XL minus 1. So the brain, we can assume the brain can calculate this. It just has to remember that on the first pass. So really what we want to know is, can we find an approximate sort of error term that makes this positive? If this is positive, then the weights are going to decrease in every trial. Okay? So can we find delta L hat such that delta L dot delta L hat is greater than 0. And we kind of want it pretty big. We don't want a lot of variance. We definitely want that positive. So it turns out that we can. Well, there's one thing we can do. It turns out that really only signs matter. So remember, the true delta L, I'll call it delta Li. So delta Li equals a sum on J of phi prime of H I L W I J L plus 1 transpose times delta J L plus 1. Okay. So we can think of this as suppose instead of using this, suppose I approximated this by the sum on J of the sine of phi prime of H I L W I J L plus 1 transpose delta J L plus 1. Okay, and suppose I did that. And in fact, because this term is a gain function, it's always positive. Phi is the increasing function of HL. This is equal to the sum on J of sine W I J L plus 1 transpose delta J L plus 1. Okay. And so the question is, when we do that, do we get the sign right? And it turns out that so basically, we're going to write delta LIL hat. Okay. Something seems a bit off. So the question we want to know is delta IL hat sort of this product going to be positive? I'm beginning to worry now that it's not. So what we really want to know is okay, I'm beginning to worry that I made a mistake. Okay, so what we want is that the angle between the sum on J between, okay, so think of this as the sum on J of some vector Vj delta J L plus 1. And this equals the sum on J of sine Vj delta J L plus 1. Okay, the question we want to know is the angle between Vj and delta J L plus 1. About the same as the angle between Vj and delta J plus 1. Oh, sorry. Sine Vj sine Vj and delta J L plus 1. Okay. Because it's about the same, then it's going to give about the same answer. Okay. And so what we can do is compute basically the cosine, oops. The cosine of the angle between the absolute value or sine term is the sum on J of sine Vj delta J L plus 1 divided by, I have the feeling I'm doing something wrong. We keep going. I may have to abandon this because absolute value, so sine of Vj squared delta J L plus 1 squared. The sum on K of sine of Vk squared times the sum on K of delta J delta K L plus 1 squared. And the cosine of just the angle without the sine is the sum on J of Vj delta J L plus 1 over the sum on J square root sum on J. The sum on J of Vj delta J L plus 1 sum on J Vj squared. Sorry, sum on K. Squared. Sum on K of delta K L plus 1 squared. So the difference is really in the absolute, in the sign here, the sign versus this And so I've sworn this worked out this morning. Something is a little bit off. I don't know what it is, but I'll fix it next time. So you can show so these are close. I must have made a mistake. Explain why next time. Yeah, my plan I can see isn't going to work. It's not so surprising, right? The sign and the value. And so really all you need, the point is that all you need is a sign of the weight. Okay, this was actually shown in a paper not long ago. And that's kind of nice because if you go back to this picture, the sign is always positive. Okay, so it turns out if you want to run backprop in the brain, at least across areas, so across areas, like, you know, this might be V1, V2. The update rule for delta H or delta IL hat is basically, which is should be the sum of basically sum of J of sine W IJ L plus 1 transpose XJ L plus 1. Sorry. Delta JL. And that goes basically to the sum on J of delta JL. Okay, because the sign of this is always positive. So you can propagate, you can run backprop. It's a massive improvement, right? Because really all you have to do is send back. So what has to be sent back in this direction? You need to send back average error. Okay, and intuitively, now it makes sense. If the average error is positive, you want to decrease the weights. If the average error is negative, you want to increase the weights. So it becomes a really, really, really simple update rule. Okay. Now we still have the problem of in each pass you have to remember the activity, but that could be done in principle. That's not so hard. So backprop. So this hasn't really. There've been lots and lots of methods for trying to fix backprop in the brain, but using the fact that the neurons are positive hasn't been explored that much. And honestly, weights are positive. It's probably the answer. Now within a recurrent network, so within a network, of course, weights can be either positive or negative. Okay. However, each neuron still knows. So within a network, more complicated. So you have to run something called backprop through time. Which is really just the same as backprop. You take your network that we wrote here, instead of each layer being sort of being a layer, each layer is labeled by time. So this is time. You basically unroll a network. This is time t. t plus delta t plus 2 delta t. All the weights are the same. They're tied because it's really the same network. And you can derive backprop using that quite easily. But even in this case, each neuron is either, so each neuron knows sign of its outgoing weight. And that's really enough to know how to update. Okay, so let's take a 5-minute break. And maybe I'll figure out what's up with the signs in that time. If you have any questions, feel free to ask. Otherwise, I'll be back in 5 minutes. Okay, notes from the previous page. This page. Yeah, so I cannot figure out what's going on with the sign. I'm very sorry about that. Hopefully I will work it out next time. Well, definitely work it out next time. Okay, so we're going to switch gears just a little bit. And we're going to talk about transformers, mainly because I think everybody should know about transformers since they have been dominating the news yesterday. So transformers, we can also think about, there's also been effort to figure out whether transformers are implemented in the brain, and we can see that there are problems. So these are basically architecture behind all these language models, or almost always language models. They're actually being used in all sorts of places now. ChatGPT. And it'd be kind of nice to know what they are, just to demystify them. And so what these networks do, at least with languages, is they take a bunch of words. These are words. This is word 1, 2, 3, word N. In the simplest version, so this is the input. And they try to predict word N plus 1. So predict word N plus 1. Okay. Now, how might you do that in a network? So the first of all, you have to encode the words. It turns out there's something called a word embedding. Been around for a while. So word, any particular word sub I basically gets transformed to some vector, v sub I, which is, I think, 64D. I could be wrong. Or maybe it's 128. It's some sort of high dimensional vector, I'm not really sure. So word embedding, this has been around for a long time in these language models. So basically what you do is you take as input V1, Vn, and the output is Vn plus 1, which then you can turn back into a word. So we're not going to worry too much about these steps, the embedding steps, and the unembedding steps have been sort of been around for a while. Instead, worry about this transformation. So we're going to focus on this transformation. Now, the easiest thing to do, so first of all, the first thing that is always done in here is basically an xi equals, basically it's vi and then some position pi. So this is a position in previous sentences. So it's basically just some encoding of this 1s, 2s, 3s. That's useful, right? If you want to produce some output, you should need to know about the positions. And so, if we were just running, vanilla in the old days, people ran vanilla. Actually, they ran recurrent networks, but that's a bit of a detail. So you could put in to your network with basically x1, x2, xn, and we could put these in. These are all vectors, of course. So you can spit them into a network, and then you could just basically run any feed-forward network you want, or recurrent network, and eventually spit out this end v n plus 1. Okay, so this would be a standard approach. And transformers just make one small twist to this, okay? Rather than putting in xi, they do something a little more clever, and they put in, so the input is oi, and oi, oops. These names are inherited from the paper, is the sum on J of basically softmax exp of x I dot some matrix dot xj divided by the sum on m the exp xi dot some matrix dot xm times xi. Sorry, times xj. Okay, and this is learnable. And that's really the only difference. And you can kind of see what this does. So this is a softmax operation. So basically, if you take this term here, so the sum on J of this whole term, exp of xi dot gamma dot xj over the sum on m exp of xi dot gamma dot xm, this equals 1. This is normalized. So basically, instead of picking out, so in the previous slide, basically just some xj, say x2 went into this thing. Instead, it would pick out x2 and it would also pick out some other x's, right? Now, when xi equals xj, this is maybe pretty big, depends on gamma. But for other x's, it's gonna include them as well. And the idea is this learnable gamma. So gamma expresses some kind of similarity. some kind of similarity. Of similarity. Okay. And that's, I mean, it was basically a tweak. I don't know how people came up with this. They came up with kind of sort of amazing things, and it just works really, really well. It's also, and so there's sort of an added twist. They included a weight here, W dot, which is also learnable. Just give it a little more flexibility. And so what happens is these OIs, so the network looks like this. So the O's, O1, O2. So basically X goes to O's, ON. It goes in, and these O's go into a network which spit out an X on layer 1. And that goes to a new O, a new set of O1, O2. New O's. So this goes to an O, and layer 1. And then, and so you can have multi-layers, 6, 12, it's not uncommon. And these things just work insanely well. They're also easy to train on, right? Because if you look at this, you know, getting from the internet, getting the next word is easy. And sometimes instead of predicting the next word, they actually predict several words ahead. They have all sorts of tricks to make this work pretty well. But now you don't have to really label data, it's labeled for you. You just scrape the internet, get billions of sentences, you feed it to the transformer, train it, and it just works really well. Now, one thing to keep in mind is that because of this term here, so this is basically this term here, oops. So this is the sum on, you know, LM of xi. This is vector xi, the elf component, gamma LM, the vector xj, the mth component, okay? So this is quadratic. In number of words. Okay, which is a bit of a downside. So Chat GPT uses, I was told, so I don't know, I have not verified this, but Chat GPT uses 2,000 words. And they're not really words, they're called tokens, so they can be a little more complicated, but basically uses 2,000, and 2,000 squared is 4 million, right? So if you want to run this thing, you know, running these 4 million computations per layer, if you have a lot of layers, you're kind of limited. And so the way you can check this is if you use ChatGPT, ask it to remember something. You know, the name of a person, a cat, remember, I don't know, the example somebody gave us, it said, they told ChatGPT to remember the word armadillo. They asked it to count to 1,000, it could still remember. But if they asked it to count to 2,000, it would forget. Because it basically throws away everything it's seen before that, okay? So these are transformers. It's just a really standard network with this addition of this term here. And it made it, for reasons people do not understand, very, very powerful. Okay, and you kind of, it sort of makes sense. If you want to do really sort of translation, if you want to make sense of the written word, you need long-range correlations. You need to remember what happened, you know, several paragraphs earlier. And that's what this allows you to do in a way that, I mean, in principle, if you go back to our network with the x's, in principle, you can also remember it in the past, but transformers just work better. And as usual with deep networks, why it works better is unknown. Okay, so that's transformers. The other thing I want to talk about is unsupervised learning. So far we've been talking about mainly supervised learning. Mainly supervised learning is what we've talked about so far. But in fact, like I said, in the brain, it's really all unsupervised. All your brain gets are spikes. Nobody tells you which spikes are good and which spikes are bad. The brain has to figure it out by itself. And unsupervised learning is really, it's finding structure in the data. In the data. And most data has tons of structure. If you look outside, I mean, there are buildings and trees. The world is not just white noise, which you would make no sense of at all, but there's lots of structures. You see the same things over and over again. And you should be able to, just by looking around, make sense of the world. Now, so a simple example. Suppose you had, two variables, x1 and x2. You get samples of this from the world, and what you find is, you get samples like this and samples like that. Maybe samples like this. You would probably say, there's structure here, right? This is one, refers to one thing, refers to something else, refers to something else, okay? And you'd say that, okay, you won't know what they refer to, but you realize that those are probably different things, where within here, there's not a lot of structure, at least not a lot of obvious structure, okay? And you can treat this, for instance, you can treat this as, P of x, x1, x2 equals a sum on mu, pi mu is a probability, and then P mu of x, okay? So P mu of x, for instance, might be a Gaussian. EXP is a common mixture of Gaussian models. So x minus, shouldn't even use the word mu, x mu, that's its mean, dot sigma mu inverse dot x minus x mu over 2 over normalization. Determinant of 2 pi sigma mu. Okay. So this is a mixture. I mean, this is just one example, mixture of Gaussian model, and there are ways of fitting unsupervised data, the means and the covariances. In this case, these would be the means, the covariance is kind of round. And the pi mu is a probability of landing each one of these things. And once you do that, right, if you want to now do classification, instead of, starting from the original problem, you get some supervision, somebody says, okay, this corresponds to a cat, this 1 point corresponds to a dog, this 1 point corresponds to a giraffe. And now you can sort of infer that all these points correspond to giraffes, all these to cats, I forget what I said, all these to dogs, okay? So unsupervised learning, in some sense, you get a lot more, you can get a lot of information, right? Labels are expensive, but you don't necessarily need a lot of labels, okay? You pre-cluster, and then once you get a single label, you can do a lot with it. Okay, so that's all well and good, but the world, if you look outside, is just, if you look in pixel space, you wouldn't get these nice, easy clusters. So instead, what people have done is say, okay, I'm going to fit, so I have data. I should not have used mu before. Data, as usual, but instead of x's and y's, you just have x. So we have x1, x2. So these are up to xp. So these could be, images. They could be text. They could be anything. Audio. Okay. You have a bunch of images and you want to model them. So model with a parameterized distribution. So call it p theta of x. And what you want to do, so p theta, these are a bunch of parameters. Actually, I'm going to call it but actually, so I'm going to sort of take inspiration from a mixture of Gaussian models and parameterize it. This is a little bit of an abuse of notation. As I'm going to write this as equal integral dz. So these are latents p theta, some parameterized distribution of x and z. Okay. And the idea is z's, this might, the z might be like a dog or a cat or anything. The idea is there's structure in the world from these latents, and the latents give us, different latents are going to give us, latent 1 gives us this thing, latent 2 gives us that, latent 3 gives us that, okay? But we're going to basically, what we don't know is what this distribution looks like. We're going to try to learn these parameters. And we learn these parameters, so we maximize, so choose parameters. And eventually we're going to see these parameters are going to be parameters of a deep network. Theta to maximize log likelihood of data. So write L of theta equals 1 over p, the sum on k equals 1 to p of log p theta of x equals 1 over p, the sum k equals 1 k equals 1 to p of log integral dz p theta of x comma z. Okay. Sorry, xk. So xk, these are data points, right? So we basically want to make data really likely under a model. It's something that's not super intuitive, right? But if our model, let's take an example over here. Suppose our model said, if our model said, let's say our model said, the model said we expect points here, here, and here, right? And our model said points over here really unlikely. A model like that would fit the data very badly, okay? On the other hand, if our model said, our points live over here, our model, basically our model was our points live over here, and over here. So that model would fit the data really well. So you want to choose parameters, in some sense latent, so that everything matches. So we actually do a good job explaining the data. This quantity here is really complicated, it turns out. So computing this integral, doing this thing, even parameterized model, you might maybe parameterize this with a deep network. It's hard. So people actually, whenever you see log in the integral, it's a classic thing. People use a variational bound. And it's once you get used to it, it's kind of, I don't know. It becomes second nature eventually. Log integral dz p theta of x comma z. We can write this as equals log integral dz p theta of x comma z over some other function q phi of z comma x times q phi of z comma x. And now what we're going to do is the log of the average of some variable, I don't know, y, is greater than or equal to the average of log y. So it's not hard to show. We can just write log, actually the average value of log y equals the average value of log, average value of y plus y minus average value of y equals equals log of the average value of y plus log of 1 plus y minus average value of y over the average value of y. And this term here is greater than or equal to 0. Not hard to show. And you can always remember this because the way I remember it is that log, let's say y equals 0 with probability 1/2 and 2 with probability 1/2. So the log of, so obviously, so y equals 1, log of y equals 0, but average value of log y equals 1/2 log 0 plus log 2, and this is minus infinity. Okay. So log of the average value of y is always bigger. So we can actually, what this means is this is greater than or equal to integral dz. This is a log of the average. The average of the log is q phi log q phi of z. Oops. It should be z given x. Q phi of z given x log p theta of x comma z over q phi of z given x. Okay. So now what you can do is basically you choose q phi. So what people do is choose q phi to be easy. Q phi to be sort of easy. To be easy enough sometimes to compute the integral or do gradient descent. Okay. So this is called the elbow, by the way. Elbow, evidence lower bound. These things have a name. So you want to maximize the elbow. So now your loss. So your loss is, so L is minus this 1 over P, the sum on K of this quantity, integral dz u phi of z given x log p theta of x and z over q phi of z given x. Okay. And now you can now, so L of theta and phi. So now you can basically now maximize L, minimize the loss with respect to theta and phi. You can take derivatives, take gradients. If you choose q phi correctly, everything's easy. Q phi is called the generative model. It's mapping from x to z, and then p theta of x given z is a recognition model. So this actually kind of works. In fact, so this is called a variational inference. If you Google, this is not my face, you'll see faces generated in this way. It's tricky to run. All sorts of things can go wrong. There's a lot of effort putting into making things not go wrong. But it works surprisingly well. And we can now generate, I think, I'm not sure if it's behind Dolly, but we can now generate images, generate faces, generate all sorts of things. And the way you generate, it's kind of cool. You sample Z to generate, you basically sample Z from Q phi of Z, and then X from Q phi of seems to be backwards. From P theta of X given Z. And you can generate all sorts of really cool images, things that actually, I mean, surprisingly, often they choose this Q, even though they choose Q phi of Z to be Gaussian, they can still get this to work. So it works. It's one of these things that works that's way better than it should. Okay, so that's it for sort of the network-based learning. What I want to do now is switch gears and talk about, let me double check that it's made it to photos. Yes, it did. Good. Because I have to delete all this because that was my last. Yep. I don't know why Zoom has this weird thing. I'm going to stop sharing and start sharing. We'll talk about a little bit about reinforcement learning, which I'm going to talk about this time and next lecture, which is the last lecture. So reinforcement. And that's learning from rewards. Okay. And in some ways, it's not the reward signal. You know, if you get a feedback signal, if you move your hand and you don't, you know, you throw a ball, it doesn't land in the right place. You move your hand to catch something and it goes in the wrong place. You get sort of a fairly rich error signal. You know how far away your hand is and what direction. A reward is not really a very information-rich signal. You know, it's usually, it's just sort of a number, okay? And learning from rewards, therefore, is harder, but it's pretty important. It's one of the main things we do. So reinforcement learning, also known as RL, basically, it's sort of a formal approach to this. And in the simplest version, so the world is divided into, oops, divided into states, which we draw like this: S1, S2, obviously a lot of states in the world, S3, which is really why reinforcement is hard, S4. And then between states, there's, when you make a straight state transition, you get a reward. This is R, the reward you get from going state 1 to state 2. A different reward from R1 to 3. Okay. World divided into states. So you collect a reward. You make a straight state transition. A state transition. And you get to choose an action. Okay, so in this case, you're in state, let's take this really simple example. So you're in state 1, you can either go to, this is R1, you can either go to state 2, 3, or 4 and collect a reward, but that's not the end. Let's say you can end up doing this. There's an R2 to 4, and there's an R3 to 4. Okay, so no matter what, you're going to end up in state 4, but you can take different routes. Okay, if you're sitting here, you can go this way, straight, or this way. And now let me give you some possible rewards. Let's say this was 20. Oops, this was 100, this was 20, and this was 40. Okay. So if you're in state 1, it looks like, you collect the most reward if you take 100, but you don't. But that's you don't actually know the other reward structure. But suppose that this was, this was 30, but this was 1,000. Okay. So the optimal thing to do in this situation is is not to take the greedy approach, but to pick up a lesser reward and then a greater reward. Okay. And this kind of makes sense, right? This is sort of how the world works. If you're too greedy, if you use a greedy policy, meaning you do things that maximize your current reward, you'll never get anywhere in life. You'll spend all your time playing videos or watching YouTube. You basically have to sometimes think ahead. And the way this is formalized is that we think of the value of a state equals the average sum of discounted rewards. And the reason I say average is because basically here, there was deterministic policy, but policies actually, given a policy, you're not all or deterministic transitions. So here you got a choice of going to state 2, state 4, state 3, but it might be a situation where, your policy would be, I want to go to state 3 or 4, but when you do that, there's sort of 80% chance of going this way or 20% chance of going this way. So often in life, and this kind of makes sense, right? You make a decision, you don't quite know what's going to happen. But we can write this as, and now discounted, because future rewards, so future rewards are worth less than current rewards. Okay. So if I say, do you want 100 yuan today or 101 yuan in 1 year, you're going to pick 100 today. Because in a year, I mean, there's lots of reasons for the discount. If nothing else, there's interest, but also the world's variable, you're not quite 100% sure you'll be alive. Okay, so discounted is discount reward. So basically, I'm going to write this one thing down and we'll stop. So V of S equals reward you get from going to. So V of S depends on a policy. So let's say you decided, what you're going to do in the state. So it's basically the reward you get from going to state S to S prime. Plus actually gamma, this is in the future, reward you get from going to state S prime to S double prime, where gamma is between 0 is less than gamma is less than 1. Can even be 0 if you want, plus gamma squared, R of S double prime, S triple prime, plus dot, dot, dot. So the farther you go in the future, the more your rewards are discounted. And the bigger your discount, the more you're going to be greedy, right? If your discount factor was 0, in the previous page, you would have basically gone straight to S4, because the future rewards don't mean anything to you. Okay. And I think we'll stop there. And tomorrow we're going to continue with reinforcement learning, and then I'll give you a specific example of decision making under time pressure. Okay, so I'll be here for a few minutes. If you guys have any questions, battery's about to die, so I won't be here too long. But that's it for today.